Examples on continuity. First example, suppose that the function f of x is equal to ax plus 2 if 0 less than or equal to x less than or equal to 1 is equal to bx square plus thrice ax plus 5 if 1 less than x less than or equal to 2 equal to e raised to twice x plus twice b if 2 less than or equal to 2 less than x less than or equal to 3 and is equal to cx plus 3 bracket square plus twice ax if 3 less than x less than or equal to 4 is continuous on the interval 0 to 4, then find the values of a b c. Now given that if is continuous on the interval 0 to 4 means what? It is continuous at end point also, that is it is continuous at 1, at 2 and 3. So since it is continuous, this implies, now since f is continuous on the interval 0 to 4 implies f is continuous at x is equal to 1. So this implies limit x tends to, this implies limit x tends to 1 plus of f of x is equal to limit x tends to 1 minus of f of x. So this implies limit x tends to 1 x greater than 1 of f of x is equal to limit x tends to 1 x less than 1 of f of x. Now for x greater than 1 it is equal to bx square plus thrice ax plus 5. So this is equal to limit x tends to 1 bx square plus thrice ax plus 5 is equal to limit x tends to 1 f of x is equal to x less than 1 it is ax plus 2. For x less than 1 it is ax plus 2. So if we subtract the limit x tends to 1, then we get b plus thrice a plus 5 is equal to a plus 2. From this we get thrice a minus a is equal to twice a plus b is equal to this 2 minus 5, that is minus 3. So we get the first equation twice a plus b equal to minus 3. Similarly f is continuous at x is equal to 2. So this implies limit x tends to 2 plus of f of x is equal to limit x tends to 2 minus of f of x. The right hand limit at x is equal to 2 same as the left hand limit. So this implies limit x tends to 2 x greater than 2 of f of x is equal to limit x tends to 2 x less than 2 of f of x. So this implies, now for x less than 2, what is x less than 2? It is equal to bx square plus thrice ax plus 5, and for greater than 2 it is equal to e raised to twice x plus twice b. So for it is limit x tends to 2 e raised to twice x plus twice b equal to limit x tends to 2 bx square plus thrice ax plus 5. So if we simplify this, we get as we take limit x tends to 2 here, it is e raised to 4 plus twice b is equal to bx square. So it is 4b plus 6a plus 5. So this implies 6a minus 6a minus 4b minus 4b minus 2b, it is equal to plus twice b is equal to, if we take it is e raised to 4 minus 5. So this is the second equation, 6a plus twice b is equal to e raised to 4 minus 5. Similarly, now we can solve equation number 1, that is here if we say this is equation number 1 and this is equation number 2. From these two equation we can we can solve it for a and b. So to solve a and b, just multiply the first equation by 2. So we get, if you multiply first equation by 2, then we get 4a plus twice b is equal to, 4a plus twice b is equal to minus 6, and here 6a plus twice b is equal to e raised to 4 minus 5. So if we subtract these two equation, then this 2b get cancelled here, minus twice a is equal to minus 6 plus 5, that is minus 1 minus e raised to 4. So this implies a is equal to 1 plus e raised to 4 divided by 2. So this is the value of a. From this now what is here, a to find the value of b. Now since twice a plus b is equal to, since twice a plus b equal to minus 3, this implies if we substitute the value of a, 1 plus e raised to 4 divided by 2 plus b equal to minus 3, this 2 will get cancelled here, and b is equal to minus 3 minus 1, that is minus 4 minus e raised to 4. So this is the value of b. B is equal to minus 4 minus e raised to 4. Now next, the function is also continuous at x is equal to 3. Similarly f is continuous at x is equal to 3. This implies limit x tends to 3 plus of f of x is equal to limit x tends to 3 minus of f of x. So now if we take the limit x tends to 3 plus, implies limit x tends to 3, x greater than 3 of f of x, which is same as limit x tends to 3, x less than 3 of f of x. Now for x greater than 3, is equal to, for x greater than 3 it is cx cube, cx plus 3 bracket square plus twice ax, cx plus 3 is equal to limit x tends to 3, cx plus 3 bracket square plus twice ax, and for less than 3 it is equal to e raised to twice x plus twice b. So now if we take x tends to 3 here, then this 3c plus 3 bracket square plus 3 bracket square plus 6a is equal to e raised to 6 plus twice b. Now if we take 3 outside, or 3 outside, this is 9 times c square plus twice c plus 1, or there is no need to simplify this. So here say 9 times c plus 1 bracket square is equal to twice b plus e raised to 6 minus 6a. Now what is the value of b here? B is equal to minus 4 minus e raised to 4. B is equal to minus 4 minus e raised to 4 plus e raised to 6 minus 6a. A is equal to 1 plus e raised to 4 by 2. 1 plus e raised to 4 divided by 2. So from this we get minus 8 minus 2 e raised to 4 plus e raised to 6 minus if we divide by 6 by 2, then we get minus 3 e raised to 4. So this is equal to minus 8 minus 3, it is minus 11 minus 5 e raised to 4 plus e raised to 6. So this is what c plus 1 bracket square, and if we divide by 9, then this is what divided by 9, this is c plus 1 bracket square, and this implies c plus 1 is equal to square root of minus 11 minus 5 e raised to 4 plus e raised to 6 divided by 9, and therefore c is equal to square root of minus 11 minus 5 e raised to 4 plus e raised to 6 divided by 9 minus 1. So this is the value of c. Next example, example number 2. Show that function f of x is equal to show that x e raised to x is equal to 1 for some, there is x e raised to x for some x in the interval 0 to 1. That is, we want to show here x e raised to x is equal to 1 for x in 0 to 1. Here we are going to use a location of root and intermediate theorem. So first of all, we consider here f of x is equal to x e raised to x minus 1, then f of 0 is equal to minus 1, and f of 1 is equal to e minus 1. Okay, so f of 0 here less than 0 and f of 1 is greater than 0. Since e minus 1, e is what, 2.71, minus 1, it is 1.71, so it is greater than 0. So f of 1 is greater than 0, f of 0 is less than 0, and therefore since f of 0 into f of 1 is less than 0, now this function is continuous everywhere. F of x is what? F of x is, now since f of x is continuous in the interval 0 to 1, and f of 0 into f of 1 is less than 0, therefore by using location of root theorem, there exists x in the interval 0 to 1 such that f of x is equal to 0. That is, x e raised to x minus 1 equal to 0, and this implies x e raised to x is equal to 1 for some x in the interval 0 to 1. The next example number 3, if f of x is equal to mod of x minus 3 divided by x minus 3, if x is not equal to 3 and is equal to 0, if x is equal to 3, discuss the continuity of x. Discuss continuity of x. Now here, first of all, the step first, f of 3 is equal to 0. Step 2, limit x tends to 3 f of x. Now since it is a modulus function, we are going to determine left hand limit and right hand limit at x is equal to 3. So limit x tends to 3 plus of f of x is equal to limit x tends to 3 and x greater than 3 of f of x. Now as x greater than 3 implies x minus 3 is greater than 0, and this implies mod of x minus 3 is equal to x minus 3, and therefore this is equal to limit x tends to 3 x minus 3 divided by x minus 3. So it is, this will get cancelled here, and answer is equal to what? 1. So right hand limit is 1. Now if you consider the left hand limit, limit x tends to 3 minus of f of x is equal to limit x tends to 3 and x less than 3 of f of x. Now as x less than 3 implies x minus 3 is less than 0, this implies mod of x minus 3 is equal to minus of x minus 3. So this is equal to limit x tends to 3. So what is here? Mod of x minus 3. The value of mod of x minus 3 is minus of x minus 3 divided by x minus 3. So this will get cancelled here. Limit is equal to minus 1. So the left hand limit is minus 1 and right hand limit is 1, and therefore limit x tends to 3 plus limit x tends to 3 plus of f of x is not equal to limit x tends to 3 minus of f of x, and therefore f of x is not continuous. That is this limit is does not exist. Limit is does not exist, so f of x is not continuous at x is equal to 3. Why? The limit does not exist, so it is not continuous. Step number 2 fails. So now next example number say 4. Example number 4. Let f of x is equal to x square plus x minus 6 divided by x minus 2 if x is not equal to 2. Can f be defined? At x is equal to 2 in such a way that f is continuous at x is equal to 2. So we want to define f of 2 such that the given function will be continuous. So now here f of x is equal to, if we factorize the numerator, we get x plus 3 and x minus 2 divided by x minus 2. This is get cancelled here, and if we take the limit x tends to 2 of f of x, we get limit x tends to 2 of x plus 3, which is equal to 5, and therefore now we can define f of 2 here. So define f of 2 is equal to 5, then f of x is continuous at x is equal to 2. So what is the answer here? F of 2 is equal to 5. That is here we can define f of x as f of x is equal to, we can write f of x as f of x is equal to x square plus x minus 6 divided by x minus 2 if x is not equal to 2 and is equal to 5. If x is equal to 2, then f is continuous at x is equal to 2. Then f of x is continuous at x is equal to 2. Now the next example, last example, example number 5, show that the function x raised to 4 plus f of x is equal to x raised to 4 plus 7x cube minus 9 has at least two real roots. Now we want to show here this polynomial function has at least two real roots. Now f of x is equal to x raised to 4 plus 7x cube minus 9. Here if we consider f of 1 is 1 plus 7 minus 9 is equal to minus 1, which is less than 0. And if we consider f of 2, then it is equal to 16 plus 56 minus 9, which is greater than 0. And therefore there exists, by using location of root theorem, there exists a real x belongs to R and x lie in the open interval 1 2, such that f of x is equal to 0. So there exists one real root. Now we know that now since complex root occurs in pair, that is if a plus ib is root of f of x, then a minus ib is also a root of f of x. So since the degree of the given polynomial is 4, so there cannot be a 3 complex root. So this implies there cannot be 3 complex root. It is not possible. This condition is not possible here, complex roots. So this implies, that is, the given this polynomial has at least 2 real root. So this implies f of x has at least 2 real roots.